Welcome to another stream, just getting things started. Seems like Tuco has stolen my seat. Alright, so I have a few things to clean up off the desk in order to get prepared for tonight's experiment. But while I'm doing that, I can explain some of the stuff that happened off camera since yesterday afternoon's stream. Let's get all the YouTubes going on the computer thing. And Tuco, as cute as you are, maybe I can move your chair over here. Maybe I can trade places with you. How's that, little cat? All right. Happy cat, ready for some electronics. So, we're switching gears a little bit. The last stream was about this project that involves voltage glitching and talking to a microcontroller over Ethernet. And so I wanted to quickly summarize some of the progress on there, both for the stream and for the camera, well, and for the recordings, I guess, for the video editing later. And then I want to kind of clean this off and get back into something that we put on hold earlier because of some technical issues. The Facedancer, which is the little USB device emulation board, teaching it to pretend to be this debug interface that I don't have access to. And last time, we got to a point where, hi train. Last time we kind of got some boilerplate done, and we were pretty much ready to get started writing the code and having it talk to the kind of debugger that we're trying to communicate with, but then just kind of ran into some problems that seemed to be related, maybe in part to the virtual machine I was using, but I think it was mostly just an incompatibility between the Facedancer code and the macOS USB stack on this machine. Possibly even this version of macOS, but I haven't quite narrowed it down. So instead of that, instead of using the combination of macOS and the virtual machine, I thought it would be simpler to just use a Windows machine, which is what I did for the first experiment that used the slightly less explainable and simple kind of solution based on patching the Great FET board. So yeah, man, that cat is pretty. Hey, Tuco. So this setup, I changed how the video capture is done from the computer, and I threw an HDMI switch in there. So aside from the occasional last-minute HDMI garbage fest that comes out when something doesn't quite reach the timing requirements, this Rube Goldberg machine does seem to manage to deliver the video both to the streaming machine and to the recordings. And with a switch in place, I can go between the Mac that I have running the Facedancer client code and a little Windows laptop that will be running the actual debugger under test that we're trying to kind of communicate with in a fake way. All right, let's get the camera rolling. I probably already formatted that one. That's fine. What's a few write cycles between cards? Okay. Let's do a slight capture of this scenario before I disturb it too much. This is one of those, I don't know, this is probably a common point to reach in debugging where you've made so much progress and it feels like there's all this delicate stuff balanced that's just barely working, but then you realize that it's not quite going to work out and you might have to back up and change strategies entirely. It's not actually that bad, but I'm less confident that I can get these two different Ethernet controllers to be compatible with each other at such an oddball low frequency. And I don't really have, I don't necessarily have the kind of clean data that I'd really like to have that points to, this is exactly where the problem is. But it looks like I'm seeing a combination of a few different issues. And so one layer of the problem is that a lot of the time I fail to even detect the link, so then I can't even send traffic to do the test. So one way I've been kind of working around that is when I'm doing like so far I've only been testing kind of one direction at a time. So because I'm focusing on initiating the test from this Raspberry Pi and sending packets over this Ethernet interface to this microcontroller, having it respond to those packets, and then along the way doing electrical glitches. So I've got this set up so I'm initiating it from this side. So far, and to go back even further, I do have this whole thing working with a modest only 25% underclock at 30 megahertz, but I want to go lower because it's still kind of inconvenient to do good, to do nice steep glitching pulses at the frequencies I'd want for a 30 megahertz CPU core. So, and most of the underclocks I've tried that go really any below 30 megahertz have started hitting other problems. So my first intuition was that was probably related to the AC coupling and that the pulses going through the pulse transformer just, weren't retaining enough of that sharp edge to still be read as a 1 or a 0, or, some other kind of analog issue with the impedance of the pulse transformer was causing the data to stop coming through clearly once I went below. And so when I say 30 megahertz, that's the clock that the CPU is running at, but the Ethernet PHY, that would be running at like a 6 1/4 megahertz clock instead of its usual 25 megahertz. So that works fine, but any below 6 1/4, I would start to have problems that seem like they might be the transformer. So in a previous stream, we took off the transformer on both sides, tried capacitively coupling the two Ethernet PHYs, and it didn't really work by the time I had to end that stream. And in the meantime, I've done a little more experimenting, and let's zoom in a bit on what I've added. I know it's going to be annoying having multiple projects in one batch of recordings, but I'm sure I can sort this out in Final Cut later. All right, so what do we got here? So this wire here, this is not quite focusing. There we go. So these two orange and green wires are Ethernet twisted pairs. And I think I made these with orange to be transmit and green to be receive on this side up here. And then that's the side that goes to this ENC28J60 adapter on the Raspberry Pi. And then this side on the bottom, those wires I think are capable of operating in either polarity, so it detects which one is transmit and which one is receive based on which one it gets link integrity pulses on. And those are wired to this eval board with the TI chip. Oh, maybe this focus is not handling the situation. All right. So these wires, they end up going pretty much directly to the system on a chip with its built-in Ethernet PHY. I think there are some small biasing resistors there, but it looks like this has the most important components of its driver built into the system on a chip, and the resistors are relatively high value if I remember right. But I've been focusing on this side, which heads to the Raspberry Pi I've been using to generate traffic since the first route that I've been testing is trying to get traffic from this side into this side. And let me switch to the schematic for that because I have it handy. So this is the schematic of the ENC28J60 as it says here. This -H actually is the name of the breakout board that I'm using that has been heavily modified. And I took off the mag jack here, so I don't have the transformers here. I just have wires going to here and here, here and here. I also ended up taking off all 4 of these resistors, the 49.9 ohm biasing resistors here. So R3, 4, 5, and 6 are all open circuit on the board. But then I put back, and I ended up putting back very similar resistors that I could play with on the breadboard, which I also brought out 3.3 volt power to and decoupled it again. So, you know, I didn't go through this data sheet in enough detail or to see whether they had specified the electrical details of the driver, but after testing it a little bit, it was pretty clear that so I wasn't sure whether the transmit side was like a push-pull driver that was capable of bringing, you know, either side of that transmit coil both to 3.3 and to ground, or whether they were only capable of driving it to ground. Since with a center tap connected to 3.3 volts here, that's all they really need to do is to drive one side of the coil to ground and the other side of the coil to ground and kind of alternate that way to generate something that ends up looking like a sine wave at the other end of the coil. So it totally could have just been an open drain sort of driver, so only capable of connecting to ground basically and sinking current. And then when I started playing with it, it looks like, oh, it's even worse than that. It's like an open drain that leaks all the time, and so I tried replacing R3 and R4 with larger value resistors, and then I just ended up getting these very low voltages there. So it's like even when it's not transmitting, it's still sinking a decent amount of current. And there's probably like a linearity reason to do that. Like if they want to make a simple Ethernet driver and it doesn't have to be really power efficient, then it's like making a Class A amplifier if you're familiar with those. So I think the values I ended up keeping there were actually pretty close. They might have been like 75 ohms, but still pretty low. So let's take a look at that breadboard. So the orange wires on the top are the transmit signal coming in from those leaky drain drivers on the ENC28J60. And then these blue wires are just 3.3 volt power also coming from the ENC28J60 board. So I'm just decoupling the power here, and then, oh, actually I think those might be lower. Those look like 47 ohms. I think that's just what I had handy. So, yeah, I just have kind of replicated that pull-up setup and not really changed it significantly. But then I'm capacitively coupling those signals over to the kind of inputs on the TI board, which already seem to have enough biasing resistance. So, like when I look at this signal, it looks pretty good. And it took a little bit of adjusting capacitances and stuff, but I got it looking pretty good, and the TI chip receives it just fine. Not at as deep an underclock as I'm hoping, but when I'm staying near 30 megahertz, so like around, I was having some kind of weird PLL stability problem at 30 megahertz for some reason, but I went down to like 28 megahertz. And at 28 megahertz, I was able to get a packet across the capacitive coupling into the TI chip, and then the firmware responded, and then I started experimenting with cleaning up that capacitively coupled signal. So, you know, these capacitors up here are like 0.22 microfarads. I ended up just, you know, out of the capacitors I had handy, having a capacitance of 1 nanofarad on the other side seemed to work better with the different impedance of that driver, I guess. And then over here is kind of an experiment in biasing. I was connecting a power supply across this resistor and capacitor and using that to try to get a stable, like 1.5 volts or so, and I was adjusting it, but trying to see if I could set the bias point to different levels and see if I could get packets through. And I still am not quite sure what the failure is in this particular circuit because it's not completely dead. I was getting occasional packets through, but it's really unreliable. And based on how good the signal looks on the scope going this direction, I think the problem is on the receive side of the ENC28J60. So it's possible that whatever receiver it's using isn't necessarily the greatest differential amplifier, and it's just not picking up, not picking up a clean signal. Also, another thing that I've been having issues with here is not with this particular circuit layout, but I think with different capacitor values. I was actually having trouble with the, I think it was the signal coming from the ENC28J60's transmitter seemed to oscillate. So it wouldn't just go from 0 to 1, but it would actually kind of oscillate from 0 to 1 and then oscillate back down from 1 to 0. Which also kind of makes me wonder what the driver circuit in the ENC28J60 looks like. Because I'm certainly no analog guru, but I can't think of how just like a plain Class A amplifier would oscillate like that unless, maybe it's causing something earlier on in that phi, amplifier, like something that might have like an inverted phase to it, like it's causing something earlier on to oscillate or to have a kind of corresponding change that then introduces an oscillation because it closes the loop. So I don't know. I mean, one option is to go and try to understand more about how that ENC28J60 phi works, but I was hitting some other problems too, which kind of gave me pause about having this communication between two different kinds of Ethernet phi, and it looks like they might be disagreeing on what the link integrity pulses should look like, and especially the ENC28J60 is giving me some really short and kind of not very strong looking link integrity pulses when it's underclocked this far. So, I mean, that again could just be a problem with the phi and it just being like something on the analog side of this, or it could be something clocking related, and so maybe there's some other like timer on chip that is contributing to those pulses that I'm not changing, or maybe I'm introducing a bug somehow that's causing the pulses to not be a useful length. And again, that's not like usually a problem, but it's borderline enough that it has me concerned. So I think my next step on that project is going to be to actually just replace the Raspberry Pi with a second eval board, just like this one, except not necessarily with all these modifications. Because basically I just want something that speaks Ethernet with exactly the same characteristics as this thing once it's been slowed down way out of spec. And probably the best way to do that is just use another one of these boards. It also helps that TI has, they have apparently designed their PHYs to decently tolerate being capacitively coupled, whereas there isn't really a clear way to capacitively couple the ENC28J60 without it really becoming kind of a pain to interface with. So yeah, my current plan is when I resume this to just start working on another one of these boards, and I could try to trigger the test entirely from one of these boards, but and even if I like just write my HTTP GET as a firmware to load on this board, it wouldn't necessarily give me all the features I want. And so first of all, I want to be able to do more than just a plain HTTP GET, because that's enough for this particular example. But the industrial controller that uses the same processor that I want to get access to, like that firmware, it's sorry, I totally lost my train of thought there. There are many layers of context there. But the goal here is to get the firmware out of this industrial controller, and one of the things that I need to pull this whole process off is a timing reference and a read from memory that are really easy to correlate with each other. And so to pull that off, I have this other HTTP request that I can put together to send that device. But I don't want to have to do all that like in the firmware for something like this. I want to be writing like Python code to send that kind of stuff. So really, I just want this to act like a dumb Ethernet adapter, but I want it to be really flexible about what the clock rates are, and I want it to specifically use this chip, or at least something that has the same silicon. So maybe one other solution is to find some Ethernet chip made by TI that probably uses the same IP core and probably behaves the same way. But I think the easiest thing to do, since I have a couple of these boards handy, is actually just to write some firmware on here that just acts as a packet bridge, and it'll, ideally just hard code the link status, just assume it's always a 10 base T full duplex link, it's always present, and then just forward packets between some other port that I can interface to the outside world and the other device I'm working on getting the firmware out of. And that's a little tricky because I can't just, stick it on USB, because if I'm underclocking that whole chip to try to replicate this situation here, then I would also end up underclocking the USB interface, probably in a way that it doesn't support super well. Maybe the on-chip clocks are programmable enough that I can make something work, but assuming I control the firmware in this case. But it might be easiest just to still bridge it back to a Raspberry Pi or something like that over SPI. So it's possible that a future video might involve doing a simple firmware for this board that acts as an Ethernet bridge back to SPI, and then writing a little program that runs on a Raspberry Pi that just acts as a bridge between that SPI device. We could also use UART, but then we have to worry about the baud rate changing anytime we change the clock rate, whereas with SPI we can have like a range of clocks that work. And then this would be most convenient if it just acted like an Ethernet device on Linux, and I could use regular packet capture tools and stuff like that. So there's a nice interface in Linux that lets you write a user space program that acts like an Ethernet device called the tap interface. So we could use that. That might make a nice upcoming video. So I think that's pretty much the summary of where this is until I put it away for the weekend. And so I'll start to clear this up, and then I guess maybe describe the other thing we're getting back into and answer any questions if people have them in chat. So I'm going to make sure 2CoCam stays aimed. Oh, I didn't really get a chance to check chat super thoroughly, but I just glanced at a comment that mentioned a horrible resistor bridge connecting them. And I'm not quite sure what kind of resistor bridge you had in mind, but I tried some things that I would definitely describe as a horrible resistor bridge. Just taking, some resistors kind of in this range, in the kind of high 2 digits and low 3 digits, and trying to bridge the two signals together while keeping them DC biased to an appropriate level, and and with at least like 50 ohms in between them, I'm not worried about the currents flowing that would cause damage. It's just a matter of signal integrity, I think, at that point. But yeah, I tried a few things like that and didn't happen upon a combination that seemed at all effective. I mean, sometimes I would get like link test pulses through, but and then the capacitive coupling actually was more straightforward than I expected it to be. Aside from that oscillation issue that I was seeing with the ENC28J60's driver, but I mean, I don't have a lot of respect for this chip, I have to say, the NC. Part of the reason I have this module is I was using it ages ago for this project where I was doing, I was trying to do like network audio with it, and so I was writing a driver that actually tried to push it to its limits a lot more than perhaps a lot of code does. And the errata list for that processor or the Ethernet adapter is pretty huge. And last time I worked with it, at least, like, there were like major features. Like, it was supposed to have TCP/IP checksum offloading, but like due to some bugs in the chip, it's just like unusably broken, so you just can't trust it. You have to do it in software, stuff like that. Stuff where some of the chip features just like have bugs where you have to occasionally retry. And so it wouldn't really surprise me if the analog, like if the PHY on that chip was not especially great as far as its analog design. It's also really power hungry for a 10-base-T chip. Like I seem to remember it wants to draw like a couple hundred milliamps, like even when it's not doing much, and so it gets pretty warm, and yeah, it's not so great. Let me put these little doodads in some kind of anti-static home. these go with the tools, and that goes with the experiments. Tuco was really in the mood to play Bolt, right? You know, maybe 20 minutes before starting the stream. I wonder if he still feels that way. Hey, Tuco. Yeah, you want more of that? Maybe he's in more of a lazy mood than I thought. All right. So. Oh, hello, Wild Mania from Croatia. Nice to have visitors from far away. It's one of the, you know, if the internet's going to have all the crazy complexity that it comes with, at least it can bring us some nice communication. Oh yeah, that scope is so loud. I don't know if all scopes are loud. I mean, my old CRT scope didn't have a fan at all. I guess I could use something like that more often. Okay. I'm not gonna like super clean this. I just wanted this to be somewhat tidy for the next segment. Okay. And subject. Back to these critters. Alright. So, I think I've got plenty of footage of this for the video already, but this is, oops, also blurry. Just for some additional context, this is the Facedancer board that we'll be working with. It's a thing that simulates USB devices. That's an MSP430 microcontroller and a USB Ethernet, or sorry, this is a USB serial adapter, an FTDI chip, and then this is the SPI attached USB host or device controller from Maxim. And that's the thing that this is all kind of remote controlling from Python. All right, so first let's just connect this back to the computer where we were running our client script and get that going again. And I've got a USB analyzer over here pretty handy, which we can use to get like a direct hardware view of what the simulated USB traffic looks like. But since we can get pretty much the same data from the software side, I'm going to do this with a simpler hardware setup just to demo that you don't need a lot of hardware to make this work. Let's save the long cable for the Windows side. Alright, that's happy. To the computer machine. Total overkill. Sure. Okay. Oh, I just saw a question in chat about what software I'm using for the video. For the editing, I'm using Final Cut Pro, but all this live stuff is happening through Open Broadcast Studio, or OBS. All right, that was some stuff I put on a disk for the other machine. And so it's a nice open source thing. It has a lot of fancy features. I'm mostly using it as a compositing and source switching and video streaming setup. But I also use it to do some of my offline recording too, since it's just a nice, like it's a pretty nice just general purpose. I want some stuff encoded in H.264 and either streamed or saved to disk kind of utility. And some of the other recording I'm doing using proprietary software, like the stuff that comes with the Elgato capturers. And I usually do my audio recording in Ableton. Anyway, what do we want here? I had the Python files kind of in progress for this, I think, in this Git repository. Yeah, so we have good fit. Git status is always great for reminding me what I was up to. Alright. I actually remember to turn off Synergy before I hit that bug again. Okay, so we went through some of this last time. Last time we talked about the kind of GoodFet project and the way that the Facedancer is kind of put together, and looked a little bit at these modules. This TCB87 device is what we started, and this is still pretty much just an empty shell. So this is a Python class that subclasses the USB device kind of generic class. And so far we're not doing anything really. I don't think this device even needs to include any interfaces or endpoints other than the default endpoint 0. I think we mostly just need to respond to endpoint 0 vendor-specific requests. So that's what this class up here is going to end up doing, but right now we don't have any handlers defined. So I think what will happen now is we should be able to load this device, connect it to Windows, load the general driver. The driver that comes with this debugger, we already verified that it's just like a forwarding driver that allows you to write USB devices from user space. So sort of like a Windows libUSB, but proprietary. And so when that device driver actually attaches, it doesn't really do anything other than maybe set the configuration on the device, the USB configuration. And we shouldn't actually see any of these vendor-specific commands until actually starting the debugger. So this skeleton of a device plus the Windows driver's kind of skeleton of a client should coexist together. And then once we actually run RD87, we should start to see commands show up here that we haven't implemented. And I don't know whether that gives us an exception or just some errors or something, but we'll see. So we can get this set up. or get this program running, and it should just kind of hang out and wait for us to connect. I can show you what it was doing on Mac OS just to make sure that we're getting the same error behavior as last time. But then I've also got a Windows machine that we can switch to, and we'll see how Windows responds to it. All right, so I think I need to set the GoodFet environment variable. Let's make sure that we're actually seeing the device here. I always like to have my USB tree visible when I'm plugging stuff like this in. So that is the GoodFet, rather the FTDI chip that I plugged into the USB hub over here. And we should see a serial port for it. Maybe not. Oh, yes. For another video, I think I glossed over this. Oh, I forget what video this was for. I needed to unload the normal FTDI driver in macOS because I needed to speak to a device with libftdi. And I think I glossed over that before the stream, but while I was streaming, there was like the get info dialog for that kext open. So I just need to load that kext manually again. I think this is just, yeah, kext load, and then Apple has their own driver for this now. Library system extensions? No, it's just system extensions. System library extensions. That's where the kernel modules are hidden. And then it's Apple USB FTDI. There we go. So that's what I want to load as root. And just type this password that I don't care if anybody knows. Okay, so now we should actually have a device. Great. 2 devices, in fact. Because I think one of those is my slower oscope is also a serial device. I think that's this one. I think just from memory, this is the one that is on this GoodFet, because I've typed it a few times at this point. So we've just got to set this environment variable. Okay, and then I think we are ready to just run the little shell of a USB device, and we'll have our own little fake USB thing that doesn't do anything yet. Cool. So the Mac's USB is connected. So I think if we plug this in right now to this same Mac, we'll start to see it continuously reset. And I'll do that just to verify that we're getting the same bug. Then I'll plug it into this Windows computer. Oh, hey cat. Oh. There we go. Oh, I think it's it keeps resetting my mouse too, which is plugged into the same USB hub. So yeah, macOS is not happy about this. I mean, it might be that the Facedancer is violating the spec in some horrible ways, but it's doesn't really read well that macOS's USB stack is suffering so much havoc. It does eventually stop trying, at least, and then my mouse is no longer resetting. So yeah, that's it's something, but it's not correct. Let's see if we get something better when I just plug this into the Windows Lappy. Let's bring the Windows machine a little closer. This is the weirdest computer. It's one of the Surface laptops, and so it's like It's like a laptop, except it's all top heavy instead of bottom heavy, which is super weird. And it has the least intuitive MagSafe I've ever used. All right. So, I think we have a fancy picture-in-picture thing that we can do here. Wave to the video glitches. All right, now we've got the laptop on the stream. Hello, chat. So let's put in, I've got a thumb drive around here, which I copied all those Sanyo tools to. There it is. This does have USB on it somewhere. I had this great like bright orange pop-up that was like, things, what do you want to do with it? But it was hidden behind the DSLR. Oops. All right, let's, might have to minimize the chat for a moment, since that's the computer that I'm using. All right. So let's just copy all this stuff locally. The touchpad on this computer is not very good, but the touch screen is actually pretty nice. I'm just not used to reaching up and touching a laptop. All right, maybe file copying is a good time for chat. Oh. Oh yeah, Tuco and I. Tuco, Micah, listen to you. We talk a lot. I'm not quite sure what the context was, but yeah, I mean, you know, I don't often know exactly what he's trying to say, but I think I often have a pretty good idea. And we talk a lot. All right, that's getting a little too meta, and this file copy is almost done. So part of why I'm copying this from Thumbstick instead of downloading it is that I couldn't quite remember where the original download was, because I got this a while ago. And the website I don't remember being very easy to figure out. I think it was kind of a maze. Still don't know why Windows makes it so hard to eject drives. Anyway. Great. So, yeah, this was just my stash of LC87 related documents and stuff. And so I think a lot of this is just data sheets I downloaded. But then this Sanyo LC87 directory, I think, is the actual, that's the actual, not the complete dev kit. And this is part of why I can't remember where I downloaded it, is I forget what they even call this, because it's not really a dev kit, because it doesn't have a compiler. It's just a debugger and example code and libraries. So I don't even know what they were thinking with this. It's kind of, I don't think it would pass for being a really great dev kit today, but maybe in its time it was all right. So anyway, mostly I want to make sure that the driver is registered with Windows here before I plug it in, because that'll just make things slightly easier. And then we can try to see if it shows up in Device Manager properly. So I think we just want this Sanyo rd87.ini installed. Is that not a driver? Oh, INF. Yeah, this is what I want. I think Is this a 32-bit machine or a 64-bit machine? Let's try this one. I have this huge HDMI Rube Goldberg machine capturing all of this, and right before I started the stream, I was panicking because I was getting some like pixel interference on the HDMI, and not just on the stream, but on the like higher quality recordings too. And I ended up tracing it to this box I had in the stream that was extracting the audio from the HDMI. Or no, it was inserting. No, it was extracting. It was extracting the audio to go to the analog mixer, and so I might just have to move that box to a different part in the HDMI tree, after one of the splitters, because maybe it's not such a great signal integrity kind of doodad on its own. All right, I'm just going to plug this thing in and let's see what it does. So I'm going to switch back to the other computer, since that has a nice terminal that'll tell us all the packets that are going on, and then we can actually see what's happening in Device Manager. And most of all, I've got this stuff installed, and so I have a USB port free. I think this only has one. Yeah, I only feel one USB port. All right. Plug. Oh, that looks nice. So, it's not getting stuck in a reset loop, and we've got all these descriptor reads, which looks right. So this is just like Windows saying, hi, how you doing? Who are you? Starting from up here. Does one descriptor read before even addressing the device? Because that's totally allowed. The device has like a default address before it gets assigned one, and it's up to the host when it assigns one, if at all. It's just, usually you see very few transfers using the default address before it actually gets assigned one. And then some descriptor reads. We could actually decode what these are if we care. I think this one is the device descriptor. That looks like well, the first one should be device descriptor. So yeah, this one's device descriptor again. And that is just a really tiny configuration descriptor because we don't have any endpoints. I think that's what that is. And then strings. So, and then it's done talking. So I would expect Windows to see a properly functioning device here. I'm going to add some more new lines just so we can see where the gap is if anything new comes along. But then I would expect some failures once the debugger actually starts talking to this. So the recorder I'm using for the stream seems to just give me these interesting glitches when I switch channels, which is fine. Then the other recorder, I was really concerned that I would end up getting these files that are really hard to edit together because there might be gaps in time. But it seems like it usually gives me separate files anytime I switch channels, which I end up liking. Oh, nice. Windows is actually still trying to deal with this device. I'm just going to open Device Manager because it would be nice to have that handy. I don't like Windows 8. I always forget what the short name of the Device Manager is. I thought it was like devices.msc, but I guess not. Ooh, this thing runs UEFI. I guess a lot of computers these days are stuck with that nonsense. So I think this EVA on-chip USB IF driver is the thing we're looking at. Oh, great, it picked up the name I gave it from the string descriptor. That is something not all versions of Windows really do, since in a lot of cases, Windows actually will just ignore the strings in the string descriptor and use the ones in the INF file. But yeah, I guess that worked out. So, I don't know why we still have a yellow bang here. Device cannot start. Let's just try replugging it just in case it's a transient problem on first install. I didn't look really closely at the Facedancer output, but it seemed like it was all just regular get descriptors. Well, let's go back and see if anything strange happens when we plug it in. Let's just restart this and get a clean trace to a file of just what happens when we plug this in once. So, let's, okay, actually I didn't want to, what I wanted was to run that and then do a hot plug. I think it will have the same effect, but I trust this more to give me a clean hot plug event. So, let me try that again. Okay. I think that's the data I wanted. And before I kill this, I'm going to go to the other machine and just make sure that the driver is still in that yellow triangle state, so that I know that this trace is correlated with that status. So, yeah, looks like that's the case. All right, now let's take a look at what we actually got. So, I think just like I was saying before, these are the device and configuration descriptors and strings. That looks pretty run-of-the-mill. Maybe this, oh. Yeah, it's possible that this thing I'm doing with no interfaces is actually just confusing the device. Let's take another look at the Windows INF file and see if maybe it is looking for an interface of some kind. Because I probably need to give it a... Yeah, I don't even know if Windows can do this. Like, I think you still have to have an interface in the config descriptor, so I might just be doing this wrong. My simple example might be a little bit too simple. So that's just this empty interfaces array, which it then uses to create a configuration descriptor. So the FTDI, for example, will create an interface that's just totally vendor specific and just have one of them. And it has these endpoints, which I don't think we need. I think we can have an empty endpoint array. So let's grab some of this to use as a template and then make something similar for our device. This is the one I'm working on. And so, oops. I keep having to also switch between the Command V and Control V kind of keys. I'm used to the VMs doing that automatically now. So we want to make an interface instance here. And copy the verbosity level. And that will just be our single interface. And I just will copy this whole line because I'm feeling lazy there. So I think here we want something much simpler too. So So maybe no endpoints. And we'll see if we can get away with not defining this function. We will, I don't even want a string. Yeah. So, and this can all be exactly the same as the FTDI device. We want a vendor-specific interface that only loads with this particular driver. We don't want Windows to ever use this device for standard drivers, or vice versa. We don't want it to load any of the standard class drivers for this device. And yeah, that seems fine. And just adapt these to the right naming convention. Great. I think that's everything we had to change to get an empty stub interface. Great, that is getting further. So now after the get descriptors, now we're getting a set configuration, which I think is the last thing that I was previously seeing the Windows driver do. So that tells the device, stop being in your low power idle state and start being in your kind of normal operating mode. And it's kind of such a boilerplate thing that I think a lot of people making USB devices don't even really think about those as being separate states, and they just always put the device in the configured state. So I think if we go back to Windows, we should see a happy driver now. Yep, that is a happy driver. Device is working properly, so it thinks. Okay, so I think the kernel mode driver is fine now, because as far as it's concerned, you know, it did its thing. It connected to the device and it set up this conduit for commands to go back and forth, and it liked our extremely minimal descriptor. But now I think the RD87 tool might have some other things to say. Oh, maybe I'll check chat since it's right here. Oh yeah, Tuco seems to like this chair partly because it's next to the heater, and he just likes chairs anyway. Like, he seems to be a good chair cat. And that chair seems to be just the right distance from the heater where it's not too warm, but when it's a cold day, which it isn't really cold today, but when it is, he seems to like it there. I mean, when he's not in nap mode, he doesn't sit still at all. He usually just wanders around exploring and wants to play with things. All right, RD87. So this is the program. We have looked very briefly at this thing in a disassembler, but mostly we're just going to be running this at the moment. Okay, well that was a quick end. It didn't even take a second to time out or anything. Let's see if it's the same every time, because this might be a software problem instead of a communication problem. So I'm guessing what this means. So it says there's a mistake in the description of device ID, and then it gives a path. So this could be a file problem, because I haven't actually run this on this computer before. Maybe I copied it wrong or something. Or it could be that it's having trouble reading the ID of the device that the debugger is attached to. So let's see if this generated any traffic. Nope. Yeah. I think this might be a corrupted copy of the program, actually, because it's not even trying to talk to the device. Let me see if I can just install this from the zip file instead of running it out of whatever this directory is. Because yeah, I think there's actually an installer you're supposed to use. I think this folder was just something I copied because like I didn't want to run the files, I just wanted to open them. Oh, here we go. LC87 series tool installer.zip seems like what I want. Oh geez, that's not what I wanted. That's entertaining. This is the, all right, well this isn't what I intended to click on, but this PDF viewer is kind of snazzy. These are the chips we're working with. They have such an optimistic view of what they're doing here. This 8-bit microcontroller is totally helping humans do brand new things. It's, oh, and I guess Easy Micon actually means something to the extent that they would put it on the front of this document. Big ol' Gaia from 2008. I think this had some mention to that TCB87 tool, but because I was going through so much of this just to find out where you even get the debug tools for these chips. Oh yeah, I think I remember tweeting this a while ago. This this I found kind of scary because oh geez, yeah, 8-bit microcontrollers have the 64K limit for usually a pretty good reason, and sure enough, you look at the data sheets. Well, how do they implement this? They have bank selecting bits all over the place, which they kind of just force their compiler to deal with, which is fine if you never have to deal with the processor at a lower level. Anyway, that's some interesting flavor here. These seem to be targeted at like televisions and rice cookers and stuff. How do you get out of this program? I guess like that. Okay, so that PDF was interesting, but this, oh geez. Okay, maybe that's what the touchpad is for. Great, a setup program. It's made of hourglasses. So that's what this is called, the LC87 series development tools, even though it doesn't actually have a compiler. Oh, I guess it has a trial version. Ugh. Yeah. So that's what we're dealing with here. I don't think we need this compiler at all. I might as well install it, but it's a pretty old school installer too. It looks like it's supposed to be full screen, but it's like inset from the edges a little bit, which is especially weird. That little tiny picture-on-a-picture window shows the Mac running the Facedancer software. And it's not quite real-time, but it's at least kind of enough to see if there are any new terminal messages. Great, the device driver installation wizard was fine with my cable. I don't think I need to open the dock folder, thanks. Okay, so I don't need any of that junk. So, what did we get for that experience? We have Sanyo LC87, which might actually run, oops. Man, these CHM files sketch me out. A while ago, you might have heard, but there were some pretty high-profile security vulnerabilities in these files. And this seems to be the only format they distribute this particular documentation in. So it's probably fine, and I'll open it on a Windows machine, but it's still kind of sketchy. The touchscreen is nice when you have giant buttons, but for like a lot of normal computer-sized stuff like this, the touchscreen is really, really tiny. But for flinging, it's fine. But then I have to go back down here to poke after I'm done flinging. Okay, that's... great. I think it's lying to us. I think actually it is connected, but it failed to talk to it because I see some new text in the window for the Facedancer. So let's see what it was just trying to do. Nice. So that is indeed a vendor-specific command that we have no handler for. So it's got a default handler that, instead of throwing a Python exception, throws a USB stall, which is also going to make the driver unhappy. So I can understand why the program doesn't really want to talk to us at this point. But this will also tell us what vendor-specific command that was. I think it's this one, because I remember them being kind of high numbers that look nicer in hex. F2. Cool. So I think at this point, there are a couple of ways to proceed. So I could do this kind of more from scratch and try to respond all of these requests with something that matches what the binary is looking for. And I already did a bunch of that work off camera a while ago in order to generate this patch for GreatFet. So I might use that as a starting point and kind of use it as a bit of a cheater list of what these commands do and how to implement them, but then re-implement them in Facedancer style code with Python. So let's grab that for reference. Let's try to keep up on chat occasionally. Oh, some couple of people in chat are curious. Specifically, Wildmania wants to hear how I pronounce my name. I usually say it Micah. I'm not like super particular about it. So like if people call me Mika, or I get Becca a lot also, which is fine. Yeah, I don't know. I also for a while went by Beth because I was just like tired of Micah, and so I kind of shortened my middle name Elizabeth to Beth, and I went by that. But yeah, I'm not super particular about that at the moment. All right, where did I put this file? I think I put this in. Yeah, LC87 toolchain. No. That's where I put it. B, the TCB87 dongle sort of .patch. Great. Yeah, so I remember we were having some trouble reading this before without the patch syntax highlighting, but this is a little bit easier with the lines color-coded. So a lot of this is not important. So we've already taken care of the vendor and product IDs. And this binary blob is the firmware that normally goes in that debug dongle. And so we're including a copy of that so that when it's read, we get the right values. But the interesting stuff should just be up here where it's handling the vendor-specific requests. So I think we've just got to implement these. And I think these are mostly going to be in the order that I found them in. So yeah, this F2, I guess, was the first thing we were finding. Let's double check that. No, maybe I already closed that window. Anyway, I think F2 is what we had. Yeah. So this is some kind of vendor-specific out. Yeah, okay. I don't remember how much of this was necessary. I think this is just some kind of like state changing command, and I noticed that, I think I noticed this in the disassembly, that the parameters mean a bunch of different things, and this particular parameter was for single stepping. but I don't think I even need to bother implementing that because I don't even get to the point where single stepping matters. So I think I'm just going to ignore that. And I think this is probably safe just to have a stub that doesn't return anything. So F2 can just do nothing. Let's remember what the format for these handlers looks like. So a number, and then name of the function, it gets a request, which has some parameters, and it can send responses if it needs to. Looks like these all have to send explicit zero-length packets to acknowledge outputs without data. So that seems fine. Let's start with something like that. It seems like these are also responsible for their own logging. It'd be really nice to know what is actually in that request, because I'd like to have this. Well, I was going to say I might like to share one handler for multiple requests, but now that I think of it, I don't know if there's actually enough overlap to where that's worthwhile. So let's start with just a very, very basic thing. And start out with just that. Just to test this really incrementally, let's just see if this gets us past this single F2 request and successfully ignores it. I'm going to start with this unplugged and then replug it from scratch again. Got our set configuration, and then I'm just going to run the debugger again. Or actually, I hadn't quit the debugger, and just to have the best chance of success, I want the driver not to be occupied when I plug it in. So I want to quit the debugger, then plug it in, then launch the debugger. So launching it. Great. So now I get past that request, and I get to a second one. So you can kind of see how this process might go. We're just fulfilling bits of the requests, or like skipping over them as best as possible. So if we look at our cheat sheet, this should be one previous from that, 241. So F1 in hex, which was, so this one's a read. So now it's expecting to get something back. And this is switching, so the value, this 16-bit parameter named value, there's another 16-bit parameter named index. That, in this case, is telling us what subcommand this is. So, and then this stage here is basically what part of the state machine we're responding in. I mentioned this a little bit on an earlier stream, but whereas you might write a USB driver on a PC to handle a command kind of in one go, so you get the whole thing, then you figure out how to handle it, then you send the response back. A lot of the times in firmware, you don't have the luxury of all the memory just to take in the whole thing, then process it, then spit it back out. So instead, you're really dealing with the state machine that needs to deal with every individual piece of the transfer. So here, this ends up running not just once per transfer, but once per packet. And then when we're receiving the setup packet, which is just that first header for the transfer, we're initializing this buffer with the data that we're going to send back in the next response packet. So this is how it's responding. So in Python, we would do this a little differently. We could just farm this out to different sub-functions using a dictionary. And then they would probably just call that same endpoint 0 send function to send back whatever packet they feel like. So I think we actually can give these better names too. I'm remembering a little more about how these are structured. And it looks like this top level command, so like F2 or F0, I think that a lot of these are further multiplexed. So these are something like, this is like a general command that hasn't really been, like I didn't bother to figure out any of these other than single step, I guess. So this is like a command that doesn't have data involved. This is a command with data going out. And this is a command with data going in. So these are all kind of like administrative things rather than like actually talking to the device under test, really. Then these other kinds of like high-level commands, these actually seem to be going to the device under test rather than just to kind of an administrative multiplexer. So, and again, they're kind of categorized by what direction the data is going in because the USB protocol cares about that. So here we have a read from the device memory, or sorry, a read from firmware. I think this is the firmware of the debug dongle itself. So this is like used when it's self-programming. And so you can read or write that. And I forget when the writes take effect, because I didn't really bother going through all the details of the firmware update procedure, since I just needed to get it to the point where the program would run. So I don't know exactly what's necessary to finalize the firmware updates, but I think this is the dongle firmware update process. Oh, maybe that's not the dongle firmware. Maybe that's the target firmware. Oh no, this is the target memory. So read target memory is... Oh, okay. So these aren't just administrative commands. These are commands that communicate with the target. I guess there are fewer of these too. I seem to remember for some reason that there was a pair of these for the dongle firmware and then a pair of them for the target. But I guess all of that's up here. So there's just a pair, well, a trio of endpoints for like in, out, and no data for these commands that include target communications and kind of internal stuff. And then separately down here, this I think is just the firmware of the dongle itself. So I guess the main reason they would have to put these into separate entire requests is so that they could have them stay compatible with the bootloader, assuming there's a separate bootloader that can run using the same protocol. So, well, that tells us how to name these a little bit nicer. So F0, let's put these side by side. We can turn off that little picture. Oh, I forget the sidebar. Command K. Command KB. Interesting. Okay. So we want this. We want to name some of these things. So we've got F0, 1, and 2. So I think we could probably figure out what they actually call this stuff by disassembling the binaries, because I seem to remember seeing strings that have a bunch of like 4-letter acronyms that don't make a whole lot of sense. But I think I'm going to call this like debug command, and I'm going to shorten this because it's going to otherwise be a really long thing. We're going to have debug commands for out, in, and no data. And so 0 is out, or sorry. Yeah, 0 is an out with data. 2 has no data, but it's still coded as an out. And then 1 is an in. And then we just have 3 and 4 for firmware out and firmware in. So logically, these, it's like we have a bunch of separate ports here, and it's almost like there are different endpoints, but it's logically separate from the endpoint system. But a lot of the time, if you had different, logical bits of functionality inside a specification or inside some firmware, you might do something like this, where you just allocate like an entire vendor request number and then do some more command multiplexing inside that. And I suspect that the firmware piece of this is just something relatively reusable that they might have elsewhere in other applications as well. Okay. And then we'll just put in some boilerplate for all these. Oh. Let's make this a little easier to edit using the multiple cursors. There we go. Oh, got my cursors out of sync. That was good while it lasted. There we go. The key combination for that I still find super unintuitive. Was I doing out first or in first? Sure, let's do out. Alright, and I also should look up how this particular USB stack deals with data going from the in the out direction. Because this is fine for an acknowledgement, but to get the actual data, I also need to figure out how to read that buffer. So I don't think the FTDI had any commands like that, because stuff like these setters, they just use the parameters baked into the 8-byte setup packets. So let's see what else we might be able to do. What does act status stage do? That sounds useful. Huh. That seems like maybe not useful for this particular scenario. And I think in this case, I don't necessarily need the data, but I might need to be able to dequeue it from the chip. So I'm just going to first see if any of these other devices do it so that I have a model. But if I need to go deeper, I might need to go look at the data sheet for this chip. So most of this is focusing on the regular data endpoints and not on endpoint 0 transfers. No vendor-specific requests here. I wonder if, handle data available probably doesn't work on endpoint 0, but maybe the path there has some clues in it. Oh, we have an IRQ handler here. I wonder if there's an endpoints entry here for endpoint 0. So maybe that's what would get this request. That doesn't look like it includes endpoint 0. So this is where we're looking at handlers for requests. Let's see how we get here. Okay, so all of that was just the relatively generic USB stuff. This file has the stuff that's actually specific to the Max, what is this? Max 3240. Why does this not have the full name of the chip in it? 42. Is it the 3421E? Yeah. The 21 is where the 21 in Facedancer 21 comes from, but then I always forget the first part of the chip. Surprisingly small file for being the hardware-specific parts of the driver. So this is where we were getting called into the kind of request-specific code later. And this USB device request is the data structure we end up getting. So I guess that answers it. We don't have to read it ourselves. It looks like this is reading, if I remember right, this data bytes. Yeah, I think this includes both the 8-byte setup packet and, oh, okay, that's up here. So yeah, the device has a FIFO in it, and it's going to just first store the 8-byte setup packet, and then after that store the first packet that we get from the other end, if there is one. So it's just concatenating those together, which is fine. And this is a little non-obvious, but this is reading the length field from that setup packet. A lot of documentation calls it W length because it has kind of a Hungarian notation, the prefixes for the length of the variable. So I guess we just have to look up how to get this out of a USB device request. I guess this has been considered, even though I don't see any of the existing drivers here using it. Maybe that file was also Max 32 whatever specific. No? USB device. Oh, nice. So, okay, so this is just something where, like, if I read this, I probably wouldn't have realized what was actually going on, because this isn't just the 8-byte setup packet, it's the 8-byte setup packet concatenated with any other data that might be there. Doesn't seem to want to store that, though, which is weird. So we might have to modify that if we need any of these values, but we might be able to ignore them all, since that's just, like, you know, the contents of the firmware. We don't need that. We can just get that from the hex file. Because this is definitely going to the trouble of, like, this is testing if this is an input. Oh, that isn't. I don't know if that test is right. It's the first byte of the setup packet, and that, I think, is set to 0 if it's output and 80 if it's input. Oh, that's right, and we're the device. I'm used to being on the other side of the USB link. But yeah, so if it's output and it has data, then we're reading it. So that's, despite this being a little bit opaque, this does seem to be doing what I would expect it to do. It would then give this something larger than 8 bytes, which it would then promptly throw away. So I guess I can deal with that for now and just worry about saving this later if I actually care about that data. All right, in that case, this is a reasonable stub for these functions. I don't need to worry about, in this out, for example, I don't need to actually specifically read that data since it's already been ignored by this request object. And then for in, that's when I actually need to give it different things because it's expecting me to. So let's have a table there, like a dictionary of subcommands. Oh yeah, sorry about the warning. The movie recording has stopped. Everybody panic. It's okay. That's just the DSLR, which I'm not necessarily using right now. I've still got the recorders going for audio and the screen capture, though. All right, what do we need? So we might be able to ignore a lot of this other than just these in commands, because the out we don't really care about. This out we don't really care about. And I think the only reason I'm really doing anything here at all is to just actually transfer the data in instead of leaving the USB core in a weird state. So yeah, I think we just need to implement these. Just those little guys. And that mostly leaves the firmware input and output down here, which I'm also going to leave unimplemented for the moment. I think if I implement this version lookup command properly, it's not even going to try to download the firmware, but we can cross that bridge if we come to it. So let's start out by just looking at which of these we have and try to put them in a sensible order. It's not very many at all. I'm not going to bother initializing that ahead of time. This is fine. might still try to give these names that are a little bit more helpful than just the hex values. So, I think I had some idea about what most of these did. Oh yeah, read target memory. I think I had a newer version of this patch at some point. I think I made a, I think I made a version of this where this was reading a separate buffer, but I think the original version of this, I just had it disassembling itself. But I think this is actually the most important command, because when we use this tool to do disassembly, this is where the data is coming from. So I think eventually this wants to read like a buffer with some actually interesting data in it, but for now I'll settle for something that is easy to easy to see, so that we just know if it's working. Let's give these a slightly shorter name. And then 4. Get status, I guess. 6-byte packet. I seem to remember it doing that a lot. 5. Oh, okay, and this one reads the identity of the device we're debugging. And so I hard-coded these. Where did I get these values? Oh yes, when I was disassembling RD87, there was a lookup table, so I could figure out what the internal chip IDs were for all the devices. Okay. Target reset. That's simple. See, doing this in Python is so much nicer than having a patch to some firmware. It's easier to start connecting these to external doodads like files and logging facilities and networks. Okay, this one I wasn't quite sure whether it was just an initialization or some kind of getter also. I think that's just setting up the one-wire interface, because it was specific to the more recent chips that have the one-wire rather than the 2 or the 3-wire debug interfaces. And then, there's that one. This is going to be interesting too. This is the version of the firmware in the dongle itself. I guess I also gave myself some notes for where in the RD87 binary it's comparing this against. This was definitely a case of it's issuing a command, it's expecting a 3-byte packet, and then I give it zeros and it's just unhappy. And then I try giving it some other values and it's just unhappy. So I disassembled a function around it to try to see what it wants, and this was what it wanted. And then I guessed what this meant by context. So I know that it wants these particular values, but I think that, yeah, I think I was able to correlate this with the lookup table that has information about each individual chip and find the one that matched the. Yeah, there's a little bit of confusion between tables for devices and tables for different versions of the firmware that runs on the dongle, because there's a little bit of overlap between the two. The LC871 devices needed this particular dongle, and so the dongle firmware also has a flag indicating, like, does it support the new protocol? So it was a little hard to tell those two tables apart at first in the disassembly, I think. Firmware info, let's call that firmware info. All right, and let's just make some stub handlers for those. A lot of these can just return static values, or just constants, if this has a handler. Alright, that should do. Have some commands, and now we'll just have some boilerplate code for these that we can fill in with more interesting handlers. And this print stuff could certainly be like automated more, but I think part of the reason it's kind of nice to have something more repetitive here is that you can modify it really easily and just add additional logging here, or change the verbosity level. Like one of those cases where I don't always think repeating yourself less is the best strategy necessarily. We have 6 of these. What I will do is at least put these in after copying. Whoops. Runaway, copy, paste. Need 6 of those. This will be so much more descriptive with these long names. Not that it matters that much, but it will be slightly more satisfying. Okay, so I think this would already get us a lot further if we just ran it right now, but I think I'm also going to add some of the easy values here. So 1E was firmware info. So that's the endpoint number, and this is a byte buffer. I think we just want that. Tuco is sleeping so much. You'd think he was a cat or something. Alright, this comment seemed worth preserving. Still not sure what those mean, but those were some relationships that seemed important from the code. device ID. I think I just picked something that seemed to have a lot of address space so that I could use it to disassemble a bunch of code. And this just seems to be a hard-coded success value for the reset. And I want this to send back something for read target memory, just in case we get that far. Oh, and we need debugger status, because that one will definitely get asked. Debugger status is 4. All right. I don't know why I bothered implementing this single step acknowledgement flag. I thought that was going to be important, but I don't think it actually gets that far. And I don't think we need it to get that far. So I think an idle status looks like 0 and then 1. Something like that. And then how big are the target memory reads? Well, smaller than our buffer here, but apparently arbitrary. So what is our length called? I guess the request has a length field. That's nice. All right, so let's make up some junk that's approximately the right length, or exactly the right length. Oh, missing comma. Oh, and I missed a bunch of colons. Okay, the driver has done its thing. Now I'm just going to restart the debugger and we can keep an eye on this. Oh, forgot to open the debugger after plugging this in. Okay, I'm opening the debugger. Ooh, nice, Python crash. Oh, right, it's not self.value, it's request.value in this case. Peanut Gallery saw that one coming. Alright, plug it in. Debugger. Ooh, so far it hasn't crashed. So I've got those 2 requests. I had a hourglass cursor briefly, and now I've got a message that the TCB87 is not connected. Let's try that again. So it doesn't time out immediately. It takes a sec. So it looks like there's something we're failing to communicate. And it finally gives us this error message, which I've definitely attached the debugger while this error message is up. It's a pretty easy way to find the code path that's failing. It might be more obvious from our logs. So we got as far as, so it looks like these 3 commands are what run every time the debugger's launched. I'm just going to verify that by launching the debugger one more time. So those first 2 come up pretty much immediately. And is the 3rd one the one that we get after timeout? Okay, I got the error message. Okay, and then after I click OK on the error message, that 3rd command happens. So the 3rd command is some kind of cleanup or some next step that is after the failure. The failure is going to be the 2nd command. So that was a 241, aka F1. Aka debug command in, which is the complicated one. And then the value, which is the subcommand here, is 9. Oh, which I guess isn't implemented. 9, huh? And length is 48. I wonder if that's a read from, oh, and direction 1 here I think means it's an in. So, and that being such a long read, maybe that's reading from the firmware memory or something. Well, I don't know why we didn't have to implement this in the previous version, but I mean, is the error behavior different? Oh, I think that's right. I think I have a different default handler here. Because I think I only actually implemented handlers for the stuff that was not happy with just getting all zeros. And I think everything else, I just return all zeros. Because, yeah, actually, now that I'm thinking about it, there's a bunch of other getters that are not in here. Like, you know, there's more than just flash memory. There's a bunch of different kinds of RAM, which all have their own different ways of reading them. And so I think I just have, I have this set up so if I'm getting one of these reads, but it isn't a known value, then none of these if clauses run. And the length up here is just set to whatever it's asking for. I just give it whatever it's expecting. And I think this buffer I zeroed, yeah, I zeroed the buffer. So let's make that the default. We can still log that the default thing is happening, but now we won't get stuck. Return some zeros. I would return something silly, but a lot of these actually probably only work with zeros because that's a good default value. Like the ones for returning target memory, I could intentionally put in values that were easy to see as bogus, but that's not what I want for all the commands. Okay. Restarting this. Plugging it in. Device driver's happy. Open the debugger. I don't know if my Python code's happy, because this is still doing the same thing. Maybe my verbosity is not actually set here. to do this. Yeah, that's better. Same behavior, just a little bit more. Okay. Great. Now I'm hitting Python errors, which is better than hitting no behavior. Yeah. Oh. Yeah, I deleted a lot more of this than I should have. Oops. Alright. I think being paranoid about the order I plug these in actually does matter. Having the debugger closed and then plugging this in and letting the driver attach and then opening it again. Oh, that's better. We've got an improvement. Let's switch. So we can already see here there's some new stuff going on. So we got, so it looks like only one default command. So that 48 zeros was read with our default handler. And then we got firmware info. So trying to figure out the version. And then we actually tried to read the firmware. And this is what the Windows program has to say. So there is a case to need for 1 or 2 minutes. I don't think we actually want to necessarily go through with this, but I'm going to switch back to the terminal and we can take a look at what happens when I press OK in this dialog, just for curiosity's sake. So hit OK now. So we're getting a firmware out request, which I'm just not at all handling correctly. And this has got another dialog box, and no, it times out. I don't know what the POC signal is in this case. Power on something or other. Anyway, so yeah. So now it's giving us this message every time we open it, and then it'll fail to update, but that's an improvement. And you can also tell it's trying to load this particular hex file. Part of the choice in the values that we gave it so far were to get to the point where it was loading that hex file and not one of these other two, the 87 or AB. We specifically want that one-wire version. Or at least I did for some of the experiments. It doesn't necessarily matter for just using this as a disassembler, but part of what I was doing here was I was actually trying to figure out that particular firmware because I was interested in it. Okay, so I think the way around this was to actually just implement that firmware read and include a copy of that TCB87w.hex. So we might actually just be able to do something similar. I forget whether I think I had converted the hex to a binary file. I might do a quick check to see if there are any convenient Python modules for reading these Intel hex files. I feel like this deja vu, like I think I've looked for Python code for reading these before, and I might have ended up just using something that I wrote in the past. Okay. So let's take a closer look at the previous patch here. So the debug target, yeah. I think I did have a newer version of this patch somewhere where I made these use separate buffers, but right now you can see these are the same. So this TCB871W.bin is the binary version of the firmware for this dongle. And down here, I'm reading it because this is where the bootloader for the firmware can return the firmware from flash memory. So it's just reading part of it in order to check for a version code. So this could even be a subset of the firmware, but especially since we're using Python, we might as well just include the whole thing because the space is not an issue. Then up here, I happen to be reading that file because I'm interested in it, but this is just the target memory that we want to send back to the debugger. So this we almost certainly would want to point to just any file we want in Python. So to get this past the point where it thinks the firmware is out of date, I'm not going to worry about the firmware write even. This version of the code had the firmware buffer in RAM, so I think I tried to implement firmware write, but then the later version had it in Flash, and so this wasn't even useful. But if I already have a firmware that the RD87 tool thinks is up to date, then it shouldn't actually even get there. And so it looks like this is just pretty straightforward. The length is just whatever it asked for. The address seems to be part of the, like it's like straddling these two 16-bit fields, which is a little weird. Or it's index, maybe it's 16 bits of index plus 8 bits from the value, like the high 8 bits. That makes more sense. So 24-bit address and a 16-bit length, and then copying it into the USB buffer here. All right, let's take a quick look for a Python module that'll do what we want. That looks promising. I mean, I basically just want to read the data into a big binary array, which sounds like this would make easy. Let's see if I can, yeah, I can install this with pip. Let's just see if that'll work. This is using Python 3, I think. Snake, Python 3. Nice little module. Okay. Oh. I guess there's already an Intel hex module in here. I guess that would make sense. Why was I getting an error in importing it, though? That's weird. Like, maybe this isn't actually Python. Let's see who's using this and if the Python 3 code in here is successfully using it. Yeah. That's using Python 2. Well, I wonder if... I guess I either need to upgrade the Python 2 only version of Intel hex that's in here, or see if I can use Python 2 for the Facedancer scripts. Really? Because I thought I gave this an environment variable telling it where, oh, and then I closed my shell, right. Yeah, that's a Python 3 thing that we came across earlier. Okay, I'm just gonna maybe remove this version of Intel Hex and see if I can use the system version. Yeah, that's better. File name or file-like object? All right. So let's start with just getting this hex file and having it handy. Oh, sorry about that. I really should have this pointing to my own fork, but I'll worry about making a patch or something for this later. Let's just copy that in. Oh. Oh, I guess I already made a bin file for this. Maybe I'll just use that so I don't have to worry about the Intel hex library at all. I think I made this because it was even just like easier to analyze than the Intel hex. If you haven't seen what they look like, let's copy that here just to look at it. It's very verbose. It's got like checksums and addresses on every line. It's not especially useful unless you want to like print it out and OCR it. But a lot of tools use it as an interchange format. So let's see if we can make this something we can just like pass a file to. All right, we'll just have that accept 2 firmware images and hand those off to the vendor code. I don't really like having those 2 parameters there. How about we just have a dictionary of different kinds of firmwares, because I think we might end up needing more images later. Firmwares. All right, and that I will populate in the little main program up here that we haven't really looked at in a while. Let's keep verbose up here. Let's make sure I get the case of this file right. I don't want it to be to only work on case-insensitive file systems. Yeah, capital T, TCB87.1.bin. And just for now, I'm going to have the target set to just some junk, but eventually this would be something you put a different firmware file in. Let's just do that for now. These target and TCB87 firmwares. And I need to figure out what the init signature is for this thing, because I want to put my own, I want to add my own parameters to that constructor. Yeah, it looks just like that. Okay, so now there are two of these firmware images that I care about at the moment, and that's this firmware in down here, and the target read up there. So the length was pretty straightforward. The address was in that split 24-bit format. So that was, I think that was value, the high bits, or the high byte of value plus the whole thing of index. So firmwares. Yeah, I think that's all this really needs. Let's put something similar up here in the read target memory command. Oh, I should be more specific about what kind of memory this is, because there are many kinds of memory. This is target program memory, which is usually flash, but these microcontrollers also come in a ROM version. And the documentation is written as if the ROM version is like the normal version, so I hesitate to even call flash normal in this chip. And how did the addressing work here? Actually, this might have been the addressing for the target program memory. Okay, yeah, target memory was... Oh. Is this only... It looks like we can only read target memory aligned on a 256-byte boundary, which is interesting. I didn't remember that detail. Then the firmware read is the one with the 24-bit addressing. All right. Yeah. I mean, it really seems like you could use the same pattern there. Like it's possible that maybe this is supposed to have that added high byte of value. I forget whether this came from just like making assumptions based on the traffic I was seeing, or whether that was something I got from reverse engineering the binary, because it looks a little suspicious. So I'm going to leave, yeah, I'm going to port this the way it's written, but that's something to maybe check into. So this is the one we want. All right. See if I have any stupid errors in that need fixing. All right, set config. Then oh, okay. Okay. This explains why I had implemented single step. Deja vu. Okay, so we're getting past the point where it checks the firmware, and you might have seen a lot more stuff flowing through in the terminal window. So I guess this is why I implemented single step. How are you, Tuco? Are you feeling 30 frames a second today? So yeah, I don't really remember the code. Like, I mean, I have some vague memories of like a big long sequence of things that RT87 was doing to check to see if the target was okay. And I guess this must have been one of them. I must have disassembled some of that code to find some of these values, but then I apparently completely forgot about that part of this project. So let's go back to the other computer. So yeah, lots of stuff here. We had any more of those default commands? Looks like still the only default command was another one of those 9s reading 48 zeros up there. And status commands, that's fine. And it totally bought our firmware image. Okay, so single stepping. Let's see what we need to make that happen, at least to the same extent that our previous version of this did. Okay, so there is a step command. That must have been the only reason I even implemented this entire F0, come to think of it. Since I probably wouldn't have otherwise even needed to have a non-default kind of handler for these. Well, this handler, okay, I'm getting these confused again. F2 is the one that I probably wouldn't have needed to implement without the step flag. I think F0, I'm still only bothering to do this because otherwise I think the USB engine would get out of sync. So I'm still ignoring all of that. And I haven't seen any of these commands so far, just in the initialization. Okay, but F2 is the one that also has subcommands, but no data. And we also need to keep track of whether a step is in progress, because I think what it does is it starts a step and then it like waits to see if it happens, or if it like gets marked as being in progress. So basically it sends a command that sets a flag, and then it checks to see if the flag shows up in a status register. So, and then I don't remember whether the flag has to be cleared. Let's see if I set this to clear anyway. Oh yeah, so okay, every time I read the status, it acknowledges the step. So it just kind of is a thing where it sends a command, and then at some future status packet, a little 1 bit will show up momentarily, and then it'll go away. So it's just kind of a pipeline acknowledge through the whole thing. Okay, so let's just implement that in Python. So we want some handlers. I'm not even going to bother with that whole thing. I'm just going to like if request.value is it's 42. Huh. Okay, that should set the single step, and now I just need to, just to make sure, I want to see that this was in the log, like as a command that we got. So we should see that it was 42 in decimal 66. Yeah, this was the single step. And then I think that was trying to read the status. Yeah. So every time it reads the status, it returns that flag and then clears it. Status. 6 bytes of status. What did I call that? That was command 4. Debugger status. There it is. This is, oh, I should just use struct pack to make these. That was going to get hairy. Oh, can I use booleans in bit shift expressions? Yes. Cool. All right. See if that helps. I think we can kind of fake our way through single stepping now. Whoops, if I could remember my commas. Oops, or what keyword to type on. Right, we have a device again. Plugging it in. Okay, that's the driver saying hi, and now I'm running RD87. And it's still failing the step test, same error as before. let's have it print out the buffer I'm giving out for status. Python 3, right, I'm still not used to that. All right, running it again. Yeah, that didn't work. At least it wasn't a new problem. Step flag. Oh, that was a debug no data request, right? Right, I put that in the wrong function. It wasn't an out. There's no data necessary to make a step happen. Let's just do that. I want to have this in charge of its own response, since that's the way most of these operate. Okay. All right, launching again. Gotta see this. Check that out. It is open. So, how much of this is real, and how much of this is going to shatter the minute we actually touch it? It's already gone unresponsive. Anything interesting? Oh, great, that would explain it. We have a bytes problem. Is that's a debug command, read target program. I think I just need to read the data from the file as bytes instead of a string, which is something that I would probably know instantly how to do if I had done more Python 3, but let's take a look. I don't want the tutorial. Our file is not built in. Okay, this is different from Python 2. This is supposed to be returning a bytes object already. So, I wonder what's up with that. Oh, this is not a bytes object. That's right. That's why it was only failing for the target. Okay. Maybe that'll help. All right, you can see it doing a bunch of requests. It's pretty slow. And then I can actually see it. I might do this again with the other computer on the HDMI switch because it's slowly populating all the windows in the debugger. I don't know if this ever stops. I think it actually just kind of continues to pull stuff. And you know, it turns out this might actually be a problem if it's this slow because I wasn't really noticing quite how chatty this was when I had it implemented with the GreatFET since it was pretty fast. But if this is spending so much time just doing reads on the Facedancer, then this might be less of a useful debugging tool actually. I mean, it might be nice to have this Facedancer version as a demo, but then I might end up having to use the GreatFET version instead, which is not terrible, but I was hoping this would work a little better. It's really slow. I'll switch to the other screen. So yeah, I don't think the flow of packets is going to stop. So it's mostly fine. Like, it looks like a debugger. You can kind of start, like, this was like refreshing just a second ago. And I mean, I'm giving it totally bogus data. So this looks even more bogus than I expect. Like, this doesn't even look like ABCD, ABCD. So this up here, the code disassembly, that's the ABCD, ABCD string that I had repeating. You can see that 61, 62, 63, 64, and so on. I'm going to start this fresh on this machine, just both to demo it and to get the video on the recorder, since I had the switcher on the other machine before. I don't currently have hardware to record multiple demo machines simultaneously. We'll see how many HDMI grabbers I end up with in this shop eventually. All right, so just to have a clean start, I'm unplugging this and plugging it back in. And then we'll just double click this. Check that out. It's like an old school like terminal emulator filling up the screen. And so that RAM view does not look right, I think. Oh, you know, I think what's going on there is I think I'm probably implementing that read by sending back a shorter packet than the host expects, which the debugger is then not really handling correctly, and it's filling in just like garbage memory. So that seems like the most likely explanation there. If I cared about having the RAM view, I might fix that. But mostly what we've got now, is this code disassembly view, which is pretty good on its own. Like, we could scroll around in here. It's really slow. It's really, really slow. Let me try to get the terminal up, because the command window is actually what is most useful here. Is that this one? Yeah. Let's maximize this. I don't know if that'll keep it from redrawing the other windows, but we can try. There we go. Yeah, I think these strings are also something related to the board identity, and we're just giving back like a shorter packet than it expects, so the debugger is kind of weird. I don't remember off the top of my head the command that gets that disassembles target memory. I think it might be just D or something, but let's pull up the help just to make sure. I don't want to inadvertently send something that's unsupported and crash this. Oh. Helps if I use the right keyboard. U for unassemble. Okay. So let's try unassemble starting from 0 to like 1,000. This is pausing. Like I think they're doing USB I/O in their user interface thread, so this is not so great. But if I can get a command through, then it's not like I have to wait for the UI to keep refreshing. Then it actually seems to be fast enough to be usable. So that looks useful. That's what I wanted. I disassembled a thing. Not a useful thing, but it's a thing. To demo this a little bit more, let's put some firmware into this. The easy firmware I have handy is the firmware for the debug dongle itself, but let's see. We can actually maybe pop up a stack. I've been so deep in this part that the reason for this is actually that I wanted to deassemble the firmware for the Wacom tablet. And so I have a binary for that handy. This is what I got off the tablet from the glitching in an earlier video. I think it was episode 15. And that's still going. It's very chatty. I think that window just likes updating its status and refreshing memory every so often. And on a real USB interface, I'm sure that would be plenty fast enough. So let's find something to disassemble with our new toy. Wacom firmware extract. There it is. I've got a couple of versions too. In fact, this is actually maybe an opportunity to try something new. I have these two different versions of the Wacom CTE50 firmware, and I got both of these with voltage glitching, and I've already checked these images out. They're good, clean images. The 1.16 version on the right there, I've already done a bunch of reversing on, and you can see these text files here. And so I think I might end up wanting to follow in the footsteps there, because that's where I want this video to go, is to document this work that I've already done. But it might also be fun to load this earlier version in, which I haven't really done much with. I guess I already disassembled it. We can peek ahead and look at the end product that I'm trying to get out of this step. That's this annotated file. And this is not as annotated as the other one, but this is basically what happens when I load the binary in there, then interactively disassemble all the chunks of code that I find and paste those results into a big text file. That's the easy way of doing this with a Facedancer and no IDA. So that one is not especially commented. This other one that I did with version 1.16, I think already has a lot of notes in it. So, yeah, interrupt tables and then a bunch of other stuff going on. Multiplexer controls. Anyway, I'm not going to go through all of this firmware, especially not right now, but we will be getting a little deeper into this later. But this is pretty much what this stuff looks like. It looks a little bit like, many other 8-bit architectures. It's, got an accumulator, it has loads and stores. Yeah, it's... what else is weird about it? It has like a weird stack that it uses for 16-bit operations. I don't know. Like, it's a basic 8-bit CPU that has some features to make 16-bit math a little faster, I guess. But most of them are like that. Most 8-bit CPUs, people want to be able to deal with numbers like larger than 8 bits. All right, so let's just grab this binary for version 1.13. Yeah, let's just stow it there for now. CTE 450, 113. Okay, I think that should be it. We run this and connect it back to the Windows computer, and then we should be able to disassemble the firmware that we captured in the earlier glitching experiment. Right, make sure the debugger is closed before I plug this in. I think the problem that I'm trying to dodge with that particular workaround is that if the program is running and then I unplug the device, the driver can't actually unload, so I think it kind of like plugs up one of the driver, like it depends on how the program actually finds the device, because if the program is smart enough to look for the device that's actually active and not like a zombie device that was held open previously, then maybe it's fine. But I think what's going on is the driver can't delete like its instance of this device when I unplug it because the program is still open. And then if I plug it in again without closing the program, the device still exists, but it's somewhere that the debugger can't find it. So I'm going to plug this in, conceal that, and then I'm going to go ahead and switch to the Windows machine so we can see all of this. Oh man. Yeah, I'm not used to the tiny targets on the touchscreen. It's good when things are big. Oh, you know what? I think there's a pen for this. Is that what this is? Oh. Oh, that helps. That's great. Okay. Here I am learning about pen computing. Okay. Let's open this up if we can. That doesn't seem to have as many windows. Oh, I guess it saves the layout, so it's just one big terminal window. Okay. That was concerning at first, since I was expecting all the other stuff to pop up, but anyway, let's just try unassemble, since the other stuff is slow and uninteresting anyway. And I know that's right under Tuco. Maybe I'll momentarily switch to the other input that gives us a full screen view. Alright. So, big full screen console thing. We do unassemble starting at 0 and not going very far. Such slowness. Come on. Okay, maybe this doesn't need full screen. Let's try. Ooh, I think something is very. Oh, it's not hung, it's very slow. I'm going to try to restore this to the default layout really quick. And then maybe restart it. Okay. Got a lot of clear memory at the beginning. Is that real? No, that's right. Okay. That's also not at the beginning. I forget where this starts, but I think we've got an IVT at the beginning. So I think 0 is our reset vector, and then we've got a few other interrupt vectors around here. I think it's safe to switch to the terminal window at this point, but let me make this non-full screen just so that we don't have to cover up any of the other pictures. Oh, it's a good thing that the window manager has to ask user space for permission every time a window moves. Okay. I mean, I'm glad this works, but I'm also annoyed that this is so slow. Yeah. This might not be really fast enough to deal with in a demo situation. Let me make sure it didn't just outright crash. Oh, it's doing some stuff. Well, if this does turn out to be unusable, like I can go back to my great FET hack and demo the actual disassembly process using that. And at least now I have a couple of versions of the same fake dongle that I could demo in different ways. But let's see if I can at least get to the point where I'm showing disassembling the IVT, because that's interesting, because we have to worry about offsets into, like, part of the reason I can't just have an offline disassembler where you just give it everything that we know is code and it comes back with a nice listing. You don't necessarily know where the beginning of each instruction is, especially in the IVT. So in the interrupt vector table, that's where the hardware will just branch the processor to a particular address when an event needs handling. And those numbers tend to be, at least on this processor, not really, like they won't really automatically synchronize most of the time. If you just start unassembling the code at the beginning, you won't really get a clean interrupt vector table. So you have to kind of specifically line it up at several points most of the time. Oh. Is this user win? Is that what I'm looking for? Maybe I just have to make this bigger so I can see the window under. I don't actually know what they call the terminal window. It's like, I don't think it's any of these. Is it user? This reminds me of, you know, when web developers are talking about testing web apps for really, really slow connections. I often found myself, like when I was working on like USB drivers or graphics drivers, finding myself, you know, wishing that apps were written to deal with very, very small amounts of bandwidth to the USB driver or to the GPU, so that that stuff could be constrained a bit to make it easier to debug. All right, maybe we want a different layout. Okay, it is the user window we wanted. It was just off screen before. Okay, so besides that unassemble command, I also want, I want to know the command to read memory without unassembling it, because I also just want to be able to hex dump stuff. That was super useful too. I think there was something like examine memory. D and friends for dumping program memory. I think we want dB, mostly, for dumping bytes. Okay, and man, I wonder if I can speed it up by just closing these windows to get it to not automatically refresh all this stuff. Oh, I think it might be getting faster already. Very slightly. Maybe. I don't know. I still think the problem is just that something is timing out in the UI thread. Okay. On-chip debugger. So we can db to dump memory in hex, I guess. Great. So those Fs are uninitialized memory, and this should just match. I mean, I'm not going to go look at it right now because it's probably obvious, but if we just looked at that .bin file that we pointed the Facedancer code at, this is going to exactly match that. So then if we start unassembling, for example, at address 0, and then I think there are different ways to specify how big the unassembly is. Like, I think you can give it an address range, but there might also be a way to give it a number of instructions. Let me see if that's possible, because that would be more useful right now. Okay, I guess by default it just does 10 lines. That's fine. So what I want, if I unassemble starting at 0, that'll give me the reset vector, and it'll also give me this next vector at 13, which we can see up here. That's this 20D227. So then if we want the next one, that'll be over here at, well, let's say, what if we just tried unassembling this straight through? Let's find the first misalignment, because that's what we actually care about. So we start at 0. We also want something to start pasting this into. I'm going to plug in my external mouse, because I can't really deal with any of... Oh, there's only one USB port. Maybe I won't. I mean, next time I'll use a USB hub, maybe. It's just, most pointing devices are annoying with it being this slow anyway. Oh, is that what we wanted? Yeah, so I'm looking at this U 0 to 100. And what I actually want to do is just copy this, starting here. Okay, maybe I'll switch back to the Great Vet. This is too painful. So most of these are staying aligned. So this is all we need. Let me copy this. Oh, thanks, Notepad. I don't have a real text editor on this computer right at the moment. Maybe I should install a real text editor, because this is bad. Maybe this is good enough. Okay, anyway, some kind of text editor. And so this starts off fine. Like, we've got, this is a real reset vector, and then here's another vector. There's an interrupt vector at, hex 13, another one at hex 1c, and if we looked at the data sheet, most of these are in the data sheet. I say most of them. Well, I guess both of these firmwares have a little bit of undocumented hardware. The Wacom firmware has its Wacom scanning engine, and the debug dongle has the one-wire communication hardware, which both seem to be somewhat custom. So these are mostly fine, but the first misalignment is right here. We can see that the problem here is when we have unused bytes, it tries to disassemble them as a 2-byte long instruction, which is bad because there isn't necessarily an even number of unused bytes in there. So it happens to work out for these first couple, or for the first one, but then right here we end up having this kind of slurp up this 20 byte that it isn't actually supposed to include. So we actually want to discard that and start unassembling again at 1B. And we could include that extra FF in there if we cared, but since that's just padding, I'm not going to bother. Okay. So then unassemble 1B. Okay, so I'm not going to go through all of this, but you get the idea how, especially in areas like this where the instructions are not contiguous, you end up having to kind of find the gaps and move past them. This gets a lot faster later on because most of the functions are fairly contiguous, and this compiler, like a lot of architectures will have like a function, and then right below the function there'll be a pool of data that function needs, because a lot of the instructions, there's a variant that makes it smaller if the data is close by. But in this compiler, it just seems to throw all the data at the end. So once we actually get into the functions, things get a little nicer. So let's get a little further in and just watch it get a little nicer. I think we can just hit U. Let's start from the reset vector that we saw up there. So that was 172. So this is going to be not necessarily the main function, but something close to it, like the startup code that then calls main. So we could get that U172. Great, so this is going, I wanted more than that. I thought it said it would, 10 lines. Yeah, 10 lines is not very much. Let's get a little more. So you can see that this is a pretty variable length instruction set, which is a little bit annoying if you don't have things lined up. Some of these instructions are like 4 bytes for like a long branch, but a lot of them are small. Oops. All right, so here we see, we can see the function prologue up there. And so let me just compare this side by side with the side by side. I guess I don't have it on this computer, but we can go back to the other computer and okay, so this terminal is really painful to use right now because of the USB slowness, but I think I can illustrate the approach by looking at the end result on the other screen. All right, let's be done with this for a moment. All right. So let's take a look at actually the 113 that we were just looking at, because it's a lot less annotated, and it's more like just the process I was just trying to talk about rather than a lot of stuff after that. So the kind of manual step that I went through using that terminal, but without all the slowness, was to kind of roughly separate out code and data. So the interrupt vector table, for example, it's a little tight because you have all of these separate little instructions that are separated by kind of a random amount of space. So I just ignored the space between them and got just the jump instructions. And down here, I forget what this is, but I think I saw a pointer to it that indicated this was a data table. So I just hex dumped it. And then down here is the actual startup function. So what I was just trying to do was, starting with this jump up here at the reset vector, I was trying to follow the reset vector and unassemble the startup code, so just see what the CPU does when you first power it on. And that took me down here to 172. And so one of the first things you can do with this is just start pasting in big blocks of code and trying to separate them into functions. And there were a couple of ways I did that. There was like a Python script that I wrote just to find all the call targets and add a little bit of white space before them to make them easier to identify. I also went through and just ended functions when there was a return, or in this case, an unconditional branch. And this is kind of a mix of stuff that a fancy disassembler like IDA can do automatically using a recursive descent algorithm, and stuff that you kind of have to do with some manual assistance. So here, for example, is a big data table. This is actually a bunch of different bits of data, mostly USB, mostly USB descriptors and related stuff. There's more functions. So that's pretty much what this ends up leading toward. So I think that's pretty much getting to a good wrap-up point for this video. I wanted to go through the process of how to actually, fake out that USB device and use that to do the disassembly. And the actual demo of the disassembly didn't work out quite as well as I hoped, but I think if I need to do any more demoing on there, I'll just use the good FET that I did earlier that's faster, or the great FET rather. So I think on the next stream, let's see, how late is it? It's 9 o'clock here. I'm not feeling quite super tired yet, but it's also seeming like this might be a good wrap-up point, since the next step here is really getting much deeper into the reverse engineering on this code. I can do just a quick preview. So this file, this has the entire disassembled ROM. I think this was 16 kilobytes, which you can tell based on the data sheet and based on just how much of the memory space is being used. And I think this was pretty full. There are also some kind of larger divisions here. For example, this version of the firmware I think includes a bootloader, whereas the 1.16 version that I've looked into much closer doesn't really include a bootloader, and it's a mask ROM version. So we can start looking at the overall structure of this. It's easy to start following like where the processor goes by looking at the entry points, and if we know, for example, what pieces of hardware these correlate with, we can try to figure out, like if we're interested in USB traffic, we can look at the USB interrupt and then start to decode where it's processing different interesting USB commands. So I've already done a bunch of that in this other annotation of the 1.16 version. Oops. So yeah, so I've labeled all of these. That's the reset vector, a bunch of timers, and then a couple of different interrupts related to the USB subsystem. And some more data tables. I try to just write down everything I know. So I don't know exactly what's going on here, but I know that this table is used for like clearing and copying memory during initialization. And it's not like it would be that hard to figure this out. It's just a lot of times it's not even really worth it. You get a feel for what something is, and then a lot of the details don't really turn out to be important, so you don't have to go that deep. But I think in this case I at least like separated it out into, this looks like a 16-bit field and this looks like an 8-bit field, but haven't actually gone through what the fields are yet. I have some USB descriptors, a lot of lookup tables and stuff. So a lot of this is not really documented much, but then other stuff where I put in more time, I've got some comments. this area near the bottom might have been what it was reading. Like, I think this tool chain kind of encourages you to put identifying information near the end of the firmware image, so I think this might be what it was reading to get version info earlier. This seems to be some format the tool chain knows about. Alright, I think that's pretty much it for this stream. I'm going to see if maybe Tuco wants to play, or if there are any questions from the chat that I can answer. Oh yeah, I haven't totally. Yeah, there's some stuff here. So the, I guess IDT for vector table. Yeah, I'm probably internalizing x86 bias here too, because I definitely grew up on x86, and like I worked at an x86 virtualization company for a while and didn't have to work on other processors. And yeah, I've also heard about this other alternative to the Facedancer, which is faster. And yeah, I forget which. Yeah, I think it uses. There's a version for the Raspberry Pi and a version for the BeagleBone. I think there's even a version that runs on the Raspberry Pi, but then still uses the same SPI, Maxim chip to talk USB. So I think that's actually significantly faster, just because it's not going over that USB to SPI bridge. So yeah, I might give that a shot too, just to see if I can write some code that's pretty widely applicable, but not bog myself down with as much slowness. I mean, I'm also not super worried about sharing the hacked up GreatFet code. It's just not something I expect a lot of people would be able to use, and it's really ugly, and you can't easily change the firmware images. Yeah. Oh yeah, I should also install some more stuff on this computer. There was a suggestion for a text editor, TextPad. Yeah, this computer actually was a recent gift from a fan, which I appreciate, and I've mostly been using it for like YouTube chat and admin kind of stuff, but it also happens to be a convenient Windows machine with a video out, so it's nice having an extra demo machine here too. Hey Tuco, are you into playing Bolt, or are you just zonked out? Oh, he's so warm. The heater is on. You might, when the oscilloscope is not on at least, you might occasionally hear like a whoosh kind of like gas turning on and off noise, because I'm sitting right next to a gas heater, and I think Tuco's got the warm spot pointed right at his butt. Alright, well it looks like the cat is tired, so I probably will not finish up this stream with a game of Bolt. But I hope you guys enjoyed that, this little bit of USB hackery and kind of prodding at this thing until this weird Windows program made some progress. And yeah, I hope you enjoyed this. I'll try to stream some more this weekend on some of these projects, which will turn into videos soon. So this is mostly footage for the upcoming video on turning a Wacom tablet into an RFID reader. So I still need to think about what the next steps are in planning out that video, but that should be pretty interesting. So a lot of little bits to look forward to. And thanks for everybody who's tuning in now, and thanks to everyone who watches the streams later, and I hope these are useful. If you have any feedback, feel free to leave me comments either in YouTube or in Twitter, and I definitely read them all, and I'll try to respond to them all. And yeah, happy hacking, everyone. I'll see you on the internets.